We have one part remaining, and that's chi-square test and ANOVA. So we're going to start with the chi-square goodness of fit test. And this allows us to see if a categorical variable is distributed as hypothesized or expected. It also allows us to tackle non-binary categorical variables and comparing more than two groups. So the first exercise we're going to look at is birthdays. So do you suspect any one day or set of the week to be more likely or less likely to be a person's birthday than any other day of the week? What is your reasoning? Well, generally we would think, each day is equally likely, unless we maybe have a lot of scheduled C-sections, and maybe those are going to be scheduled during the week. But in generally, we wouldn't expect one day to be more likely than another day. So below we have 147 randomly selected people. They were asked what day of the week they were born. And you can see that each, over here on Monday, we had 17, on Tuesday 26, Wednesday 22, Thursday 23, Friday 19, Saturday 15, and Sunday 25. So we certainly see some fluctuation between the days, but would this be something that is unexpected or that couldn't have happened by chance, or is this due to normal sampling variability? So, what do you think? Well, there's certainly some variation. But nothing out of the ordinary. And in fact, we have with Tuesday and Sunday the most common days. And we can also notice that Saturday and Monday and Mondays were the least common days. So what we're trying to test is if each day is equally likely. So our null hypothesis is that the proportion of Monday is equal to the proportion of Tuesday, which is equal to the proportion of Wednesday, and so on, all the way through Sunday. And then our alternative is they don't all have to be different, but at least one of the proportions is different. So when we're looking at our variable, we have over here the days of the week. And those are categorical variables. Or it is a categorical variable. We're only looking at one variable in this example. Here are our assumptions. Number one, we need to have a simple random sample. That is the case for all our inferential statistic, because if we don't have a representative sample, there's no sense in us doing inferential statistic. This is looking at proportions over here, but we have a lot of different groups. So our expected counts are at least 5 in each category. So remember when we looked at binomial, we said at least 10 successes, at least 10 failures. So we've kind of softened that down a little bit, saying that as long as we have at least 5 in each category, we're going to be okay. Now, if we use technology like StatCrunch, it's going to give us a warning if we have a lot of different values that are not at least 5. So we set up our hypothesis as we stated. So our null hypothesis being all the proportions are equal to each other. And our alternative is at least one of these is not equal or is different. So first we calculate the test statistic, which is a chi-square test statistic. This is the Greek letter chi. We take the sum of the observed values minus the expected values. We square those and then divide by the expected values. So it's actually a pretty similar calculation to what we did when we did variance and standard deviation at the beginning of the semester. We also have something called degrees of freedom again here, and this is the number of categories minus 1. So a little different to what we've seen before for the degrees of freedom. What's also similar to the T is that our degrees of freedom change, or our curve changes as our degrees of freedom increases. So you can see over here that the chi-square distribution is a right skewed distribution. So the first curve being here for 1 degree of freedom, we can see that it starts getting a little more symmetric as our sample size increases. The other thing to notice is because we are squaring these values and all our expected values are positive values, our curve starts at 0 over here. So we always end up with positive values. Or if there was no variation, then we would end up with a chi-square test statistic of 0. So the closer our observed values are from the expected values, the smaller this test statistic, and the further away we are, the further we go kind of towards the tail of that distribution. Here's a couple more properties. All values are non-negative. The distribution is not symmetric. The shape of the distribution changes for each degree of freedom. So let's fill in all those numbers down here, and we're going to go over the calculation for calculating our test statistic. So again, we had 17 observed on Monday, 26 on Tuesday, 22 on Wednesday, 23 on Thursday, 19 on Friday, 15 on Saturday, 25 on Sunday, for 147 total. Because we expect each of these days to be equally likely, we are going to take 147 divided by our 7 days, and that gives us our expected count of 21 for each day. So generally we do one of these by hand just to kind of illustrate the point, how we find the test statistic, and then we just use technology over here. So our observed minus the expected would be -4. -4 squared is 16, so that's 16 over 21, which is 0.762. 26 minus 21 is 5. 5 squared is 25. 25 over 21 is 1.19. The distance is 1. 1 squared is still 1. 1 over 21 is 0.048. This difference is 2. 2 squared is 4. 4 divided by 21 is 0.19. This distance is 2 again, so that is the same as Wednesday, 0.048. This difference is 6, so it's 36 over 21, which is 1.714. This one is 4. 4 squared is 16 over 21 is 0.762. And then we can add up all these values together and we end up with 4.714. We have 6 degrees of freedom because there was 7 days, so the number of categories minus 1. So again, our chi-square test statistic is 4.714. In order to find the p-value, we are going to use something called chi-square CDF. Our tests are always going to be right skewed because we always end up with positive values. So in order to determine the p-value, we are actually finding that tail probability. So we're going to start at our test statistic 4.714, going to infinity, and then we have 6 degrees of freedom. So on the TI calculator, we're going to go to second vars, which has all our distributions. We're going to go down to option 8, which is chi-square CDF. We are going to put our test statistic as our lower value. We are going to put a very large number, or we can do E99, which is 10 to the 99th power. So that's second, comma, button, and then 99. We are entering our degrees of freedom, which is the number of categories minus 1. We're going to hit enter, and we have 0.5810 rounded to 4 decimals. So our p-value again is 0.5810, which is greater than any reasonable significance level. So let's say we're going to use the most common one, which is 0.05. Our conclusion is always the same. When our p is low, we're going to reject the null. Over here, our p is greater, therefore we're going to fail to reject the null. Therefore, our final conclusion is there is not sufficient evidence that the proportions are not equal. All right, this was a little longer example, but we'll have some more examples coming up.